right, so here is hopefully a quick review of limiting reagents and percent yield. So we're going to start with an analogy that's not chemistry, just to get into our minds what even is a limiting reagent. So let's say that I'm making sandwiches, and my recipe for a sandwich is 2 slices of bread, 1 piece of cheese, and 3 pickles. If I have 8 slices of bread, 6 pieces of cheese, and 27 pickles, how many total sandwiches can I make? What you're probably doing in your head is some division. If I have 8 pieces of bread and I need 2 per sandwich, I can make 4 sandwiches. If I have 6 pieces of cheese and I need 1 piece of cheese for each sandwich, I could make 6 sandwiches with the cheese. 27 pickles, I need 3 per sandwich. 27 divided by 3 is 9 sandwiches that I could make. But I can't actually make 9 sandwiches, right? I'm going to run out of bread. So the most complete number of sandwiches that I can make is 4. I can make 4 sandwiches because I'm going to run out of bread first. So in this example, our limiting reagent is going to be the bread, because I can only make 4 sandwiches before I run out of bread. Lots of leftover cheese, lots of leftover pickles, but the bread will be gone. So this is the idea, the concept of a limiting reagent. So let's say that I've got 12 slices of bread, 9 pieces of cheese, 15 pickles. How many sandwiches can I make? Again, you're probably doing 12 divided by 2 is 6. 9 divided by 1 is 9. 15 divided by 3 is 5. So I can really only make 5 sandwiches. My limiting reagent this time is going to be pickles. This is kind of tricky because you might notice we actually have the greatest number of pickles. 12 bread, 9 cheese, 15 pickles. I've got more pickles than anything else. How can I run out of pickles first? Well, it's because I need more pickles per sandwich than I do any of those other reactants. So we can apply the same idea when we have actual chemical equations. So first, we always need a balanced equation. Stoichiometry is entirely dependent on balanced equations. So I'm going to throw a 2 in front of that copper. I've got 2 coppers. I've got 2 coppers, 1 sulfur, 1 sulfur. If I have 1 mole of copper and I have 1 mole of sulfur, what am I going to run out of first? Well, I need 2 coppers for every 1 sulfur, and I only have 1 copper and 1 sulfur. I'm going to run out of copper first. Copper is my limiting reagent. I'm going to run out of it first. I have a 2-to-1 ratio. I have 1-to-1 in my reactants. I'm running out of copper first. Copper is limiting. So we can think too about the maximum number of moles that we could make. So again, if I go back to my balanced equation, if I have 1 mole of copper and I have a 2 coppers to 1 copper, 1 sulfide is what this guy is, invisible 1. If I have a 2-to-1 ratio, we can knock out our coppers and we're going to end up with 1 times 1 divided by 2. I've got 0.5 moles of Cu2S formed. If I looked at my 1 mole of sulfur, now I have a 1-to-1 ratio. 1 sulfur to 1 copper, 1 sulfide. 1 times 1 divided by 1 is 1 mole of copper, 1 sulfide. Can I actually make that whole mole of copper, 1 sulfide? I cannot, because I'm going to run out of copper first. So this is another way to determine what your limiting reagent is. You can convert each of the quantities of reagent to a product and then compare. The product that is formed less is coming from the limiting reagent. So again, copper is our limiting reagent, and the maximum amount of copper 1 sulfide that I could make is 0.5 moles. So it gets a little bit trickier when we start with grams instead of moles. I have to convert my grams to moles. Again, make sure that equation is balanced. I'm going to go ahead and, because I know on my last screen I had to find maximum amount of product that could be formed, I'm going to go ahead and convert both of my reagents to moles of product, and then I'm going to pick the lesser of the 2 products as my as coming from that limiting reagent. So again, I'm going to take my 80 grams of copper, and I'm going to convert it to moles of copper 1 sulfide. I'm going to do the same thing for my 25 grams of sulfur. So, hands it into periodic table, the molar mass of copper is 63.55 grams per mole. Molar mass of sulfur is 32.07 grams per mole. I'm going to go ahead and convert, since I've got moles, I'm going to convert from copper to my copper 1 sulfide. So 2 coppers on the bottom to get my coppers to cancel out. 1 copper 1 sulfide on the top. Same thing here, but I'm going to use sulfur. I'm going to put my 1 sulfur on the bottom, my 1 copper 1 sulfide on the top. So the reason that we have these guys set up like this, I have grams canceled out, and now I've got copper canceled out. I have moles of copper 1 sulfide left. And then here I have grams canceled out. Sulfur is canceled out. But again, I have moles of copper 1 sulfide. So I can use my calculator. I've got 80.0 grams of copper divided by 63.55 times 1 divided by 2 is going to give us 629 moles of copper 1 sulfide. Whereas here, my 25 divided by 32.07 times 1 divided by 1 gives me 0.7795, and so that 5 is going to make that minus 0.780 moles of copper 1 sulfide. So I'm just going to scan to see which one is less. This is less than this. 0.629 moles is less than 0.780 moles, which means that copper is my limiting reagent, which is weird because I've got more than 3 times as much copper, but I need more copper, and its molar mass is quite a bit bigger. So we're actually going to run out of copper first. Copper is limiting. All right, so we decided that copper was limiting. I'm going to go back, and our moles of copper 1 sulfide that can be formed is 0.629 moles. So copper was limiting, and we could make 0.629 moles of copper 1 sulfide. Again, I'm going to go back. I can't actually make this much copper 1 sulfide. Even though I have lots of sulfur, I'm going to run out of copper. This is the maximum number of moles of copper 1 sulfide that I can make. So if this is the maximum number of moles of copper 1 sulfide I can make to find out my grams, I'm just going to convert this mole that I got from the limiting reagent into grams. So copper, again, on the periodic table is 63.55 times 2 plus 1 sulfur, which is 32.07. The molar mass of copper 1 sulfide is 159.17 grams per mole. And I put grams on top so that I can cancel out moles, top and bottom. Do that multiplication, 0.629 times 159.17, and we're going to get 100.117, lots of digits. I get to keep 3 sig figs, so I have 100 grams of copper 1 sulfide formed. All right, so let's do, this is actually a released AP question, AP chemistry question. Let's go ahead and balance first. So I've got 2 oxygens and 3 oxygens. I already know I'm going to have to double this because my even here is never going to match that odd number unless I have an even number here. That's going to give me 4 irons, and 2 times 3 is 6, so I need a 3 here, 3 oxygens. Balanced equation, done. Calculate the number of moles of each. So my iron, I have 75 grams of iron. I'm going to go ahead and convert that to moles. Molar mass of iron is 55.85 grams per mole. So 75 divided by 55.85 equals 1.34 moles of iron. Do the same thing for our oxygen. So we've got 40 grams of oxygen. Be careful here, it is O2, so I have to double my oxygen mass. So not just 16, but 32. I need O2, 32 grams per mole. 40 divided by 32 is going to give us 1.25 moles of oxygen. Limiting reagent. So I'm going to go ahead and use these moles that I just found, and I'm going to convert both to my product. So if I convert these moles of iron, 4 irons, and 2 iron-free oxides, 1.34 times 2 divided by 4 is going to give us 0.67 moles of iron-free oxide. If I do the same thing with my oxygen here, my O2 on the bottom, I have 3 O2s, and I still have those 2 Fe2O3s. So 1.25 times 2 divided by 3 is going to give us 0.83 moles of iron-free oxide. Since I have fewer moles of iron-free oxide when I start with my iron mass and moles, iron is the limiting reagent. So the total number of moles that we can produce, I'm going to again take my limiting, we always start with the limiting. I already have moles of that iron 3 oxide. I'm going to go ahead and convert that to grams. So iron times 2, iron on the periodic table is 55.85 times 2, plus oxygen is 16 times 3 is going to give me 159.7 grams per mole. Moles cancels out, top and bottom, 159.70 times 0.67 is going to give us 106.999 grams. Check our sig figs. I get to keep 2, so that 6 is going to turn that 0 into a 1, 110 grams of iron 3 oxide will be produced. So now let's figure out how much excess reagent is left over here at the end. So if I go back up here, I know that I had 1.25. Let me find a new color. I had 1.25 moles of oxygen. Oxygen's in excess since iron was limiting. So 1.25 moles of oxygen is what I start with. I'm actually going to use not all of those moles of oxygen. So I'm going to go ahead and take my moles of iron here, 1.34 moles of iron. And instead of converting to my product, I'm going to use this mole number to convert to my moles of oxygen needed. So I'm going to keep my iron. I'm going to get rid of it here with the mole ratio from the balanced equation. I'm going to convert my iron into oxygen, so 3 O2s. So my 1.34 moles of iron times 3 divided by 4 requires 1.005 moles of oxygen. So what I just did, this math is telling me that if I have this many moles of iron, I need this many moles of oxygen to completely react with all of that iron. I need this many moles of oxygen to completely react with all that iron. I'm going to go ahead and convert my sig figs 1.005. It would be better to do 1.01. So ignore that 1.01 with sig figs. So this is how much oxygen I need. This is how much I have. This is how much oxygen I need in moles. This is how much oxygen I actually have. So if I take away all the oxygen that I needed to completely react with all the iron, 1.25 minus 1.01, I can actually do this math in my head. I'm going to have 0.24 moles, moles of oxygen left. It just tells me amount, so we could totally leave this in moles. Mole is an amount. But let's say that it actually asked us for mass. Then I could convert that mole back to mass. We already decided that the molar mass of oxygen was 32 grams per mole. Moles cancels out, 0.24 times 32. That's going to give us 7.68 grams of oxygen left over after this reaction.